What's up, guys? This is me, Sir Ernest, and today we're going to have some examples related to the equation of motion of a particle moving under a central force field. So the problem reads, a particle in a central field moves in the spiral orbit given by this equation. So here we're asked to determine the force function. Okay, so recall that the equation of motion under a central force field is written as follows. This is second derivative of u with respect to theta plus u, and that is equal to negative 1 over ml squared u squared times f over of 1 over u. So our goal here is to determine these terms, the second derivative of u with respect to theta and u, based on this orbit information in order to determine the force function. So to do that, let us first express r in terms of u. So from here, we know that u is now equal to 1 over c theta squared. So therefore, the derivative of u with respect to theta is now equal to negative 2 times 1 over c theta cubed. And the second derivative of u with respect to theta will now be equal to 6 cu squared. Okay, so therefore we can now assemble our equation. So from here we now have 6 cu squared plus u, and this is equal to negative 1 over ml squared u squared times your f. So remember that your f is a function of u. So therefore, f is now equal to negative ml squared u squared times 6 cu squared plus u, or negative ml squared u squared negative ml squared, and then we distribute u squared, so therefore this becomes 6 cu to the fourth plus u cubed. But remember, this is not yet our equation of motion because our force function is still in u. So therefore we now go back or bring back this equation in terms of r. So therefore, this r is 1 over u. So therefore, fr is now equal to negative ml squared times 6c over r to the fourth plus 1 over r cubed. And this is the force function of the particle. As you will notice that this force function has two parts. The first part varies with 1 over r to the fourth. So that's inverse fourth power law. And on the other hand, the second term is actually an inverse u. Okay? Now, with the follow-up, that's equation 6.5.2. So from this example, from example 5.1, let's now determine the angle that varies with time. In order to do this, let's go back. Let's recall your small l. What is small l? Small l is the angular momentum per unit mass. And this is equal to r squared theta dot. And we all know that this is a constant by virtue of conservation of angular momentum. So therefore, this tells us that theta dot, which is the time derivative of theta with respect to time, and that is equal to L over r squared. Or in terms of u, that's L u squared. From our orbit information, theta dot is equal to L over c squared theta to the fourth. Okay? So now solving this differential equation, we have the following. Theta to the fourth d theta is now equal to L over c squared dt. And the integration happens from, because at time equal to 0, theta is assumed to be 0. So that means it started with theta equal to 0 with 0 angular position with respect to the x-axis. And then at a later time t, your position is at theta t. So solving this equation, we have theta to the fifth over 5 plus L equals L over c squared t, or theta as a function of time is now equal to 5L over c squared t to the 1/5. So again, this is the your angular position with respect to time. So therefore, so you will notice that this varies with t to the 1/5. We can calculate it further by getting the position function r as a function of time, or radial position as a function of time. And this is equal to c times 5L over c squared times t to the 2/5. And this came from this information. So you will notice that from here, theta is equal to or r, sorry, r is equal to c theta squared. So squaring this gives you this times c is this one. Okay, where theta is equal to r over c to the 1/2. Okay. So this ends our discussion on example 6.5.1 and 6.5.2. I hope you learned something, and see you again in the next video. Bye-bye.